Okay, we'll go on to number 23. We're looking for points of inflection and to discuss the concavity of the graph. Number 23. We have f of x is equal to 1/4 x to the fourth minus 2x squared. First derivative is 4 over 4 is 1, so x to the third minus 4x. Second derivative is 3x squared minus 4. Alright, we could factor, but I'm not sure how much that's going to help us. We'll leave that as our second derivative. Now we need to set that equal to 0. 3x squared minus 4 is equal to 0. 3x squared is equal to 4. X squared is equal to 4/3. So x will be plus or minus. Square root of 4 over 3 would be 2 over the square root of 3. Rationalizing, we will get 2 root 3 over 3. And plus or minus. So we'll set up our sign chart. Now we should have some idea of what 2 root 3 over 3 is, and I always expect students to remember that square root of 2 is roughly equal to 1.4. Square root of 3 is roughly equal to 1.7. So 2/3 of 1.7, it's almost like saying 2/3 of 18 would be 12. So 2 root 3 over 3 is roughly equal to 1.2. So we make our sign chart, and we'll have negative 2 root 3 over 3 and positive 2 root 3 over 3. And 0 definitely falls in between. 2 and negative 2 should work fine for test values, and we're working with the second derivative here. So we'll plug in negative 2 is going to give us 3 times 4 is 12, so that's definitely positive. Plugging in 0, we get negative. Plugging in 2, we get positive. So we're concave up, concave down, concave up, and since this function is continuous everywhere, we have x equals plus or minus 2 root 3 over 3 are points of inflection. And the concavity, concave up from negative infinity to negative 2 root 3 over 3, and then from positive 2 root 3 over 3 to infinity. Concave down, from negative 2 root 3 over 3 to positive 2 root 3 over 3. And that'll do it for that one. I'll bring up the calculator and we'll take a look at this. So we have 1/4, we'll put that in as 0.25, x to the fourth power minus 2x squared. Zoom standard. We'll see what that gives us. Okay, it gives us a pretty interesting graph there, and we'll just adjust. We have plenty of room on the x-axis, so we'll adjust that from -5 to 5, and get a much better picture of that. I'll put a picture of that on the workspace. Okay, so we said at about 1.2, negative 1.2, which is right about there, we have a point of inflection, and the graph was concave up prior to that, concave down after that, and then up at 1.2 roughly we change back from concave down to concave up, and so you can see the points of inflection and the concavity match our analysis perfectly there. We'll go on to number 25. Number 25, we have f of x is equal to x times x minus 4 to the third power. Now we could think about multiplying this all out, which still may not be a bad idea, but I'm going to go with the product rule here. Now the only reason I hesitate with the product rule is because I'm going to have to take a second derivative, and I'm afraid I'm going to have product rules, many of them. But let's see what happens. 1 d2. So we have function composition. We'll leave the inside alone, and that'll just be times 1. So 1 d2 plus 2 d1, and that's simply going to be x minus 4 to the third power. So let's see what happens when we simplify this. We'll have 3x x minus 4 to the second power plus x minus 4 to the third power. Now, I think that I'm going to opt for factoring this, and let's see what we get. We'll bring out the least common multiple, which is x minus 4 to the second, and that will leave 3x then plus x minus 4. What power? When we multiply two numbers with the same base, we add exponents, so 2 plus what equals 3? 2 plus 1 equals 3, and so we have x minus 4 to the second times 3x plus x, which is 4x minus 4 to the first. Alright, that's our first derivative. Second derivative, let's see how complicated this gets. We have the first, x minus 4 to the second power, times the derivative of the second function, which is just 4, plus 1 d2 plus 2 d1, and that's going to give us 2 times x minus 4 to the first times 1 d2 plus 2 d1, and let's simplify. So we have 4 times x minus 4 squared. Then we have plus 4x minus 4 and times 2 times x minus 4 to the first. So I'm going to rearrange these terms and instead write the 2 up front, 4x minus 4, and then x minus 4 to the first. Alright, we'll need to factor here. Bring out the x minus 4 to the first power, and that leaves us with 4 times x minus 4 plus 2 times 4x minus 4 x minus 4 times, let's see what we get here, 4x minus 16 plus 8x minus 8, x minus 4 times 12x minus 24, and we can factor out again from the 12x minus 24 a 12, leaving us with 12 times x minus 4 times x minus 2. If we're very fortunate, we have two potential points of inflection at x equals 4 and at x equals 2. But we don't have any room to work with, so let's see what we can do here. So we'll start a number line over here with x equals 2 and x equals 4. And we have our factored form of the second derivative. Should be fairly easy to work with. Our second derivative test values will be 0, 3, 5. And we plug in 0. We'll get negative times negative is positive, so that should be positive there. Plug in 3. We get negative times positive, which is negative. Plug in 5, we get positive times positive is positive. And so we have concave up, concave down, concave up, and points of inflection. X equals 2, x equals 4 are points of inflection. Now I'll bring up the graphing calculator. I don't know that I have room to actually store any of this, but we'll see. So for number 25, we have x times the quantity, x minus 4 to the third power, and we'll zoom standard and see what we get. Kind of hard to read that there. I will spread it out by changing my y's from negative to go from -2 maybe to 5. Let's see if that helps at all. Alright, a little bit better. And then we'll need to adjust the x's to go, the y's to go down to say -20 by 5. So let's see if that changes it. A little bit more, we'll go down to -25, or even go down to -30, so, and see what that looks like. So we can see, let's see if I can, at x equals 2, we definitely have a point of inflection, and at x equals 4. So, alright, so if I move some of that first derivative stuff over, we can see that we do have, in fact, at x equals 2, we have this point where the graph goes from being like a cup to being like a frown, and then again, at x equals 4, it goes from being concave down to being concave up. And so we were right on target again. So that'll be it for this video.